Hello, this video is on lesson 8-2 where we talk about operations with complex numbers, and it begins on page 126. Learning targets here are to add and subtract, multiply and divide complex numbers. Okay, so let's go ahead and start adding complex numbers. What if we have I plus I? So think about this for a second. I plus I. Well, you actually treat I just like a variable. And I plus I is going to be 2I. So can you see how we basically, if we had x plus x, that would be 2x. We treat I just like a variable, 2I. So if we have 4I minus I, well, that's going to be 3I. And what if we have I times I? I times I. Here we go. Well, I times I is going to equal to I squared. Again, you treat I like a variable, so if you had x times x, that would have been x squared. But there's something more that we need to know about I squared. Isn't I times I, remember, what is the definition of I? I is equal to the square root of -1. And so can't we say that I times I, or I squared, is basically the square root of -1 times the square root of -1? Right? Now, what is going to be the square root of -1 times the square root of -1? Well, let's look at these examples. This is something that you can plug into your calculators. And when you plug them in, you get that the square root of 3 times square root of 3 is 3. And I encourage you to do this in your calculators. Okay, let's keep going. Square root of pi times square root of pi, well, that's going to be pi. And the square root of 5 times the square root of 5, that's going to be 5. So notice that when you multiply two square roots that are basically the same, the answer that you get is the number that's inside the square root, and you don't have the square root any longer. And so when you're multiplying square root of -1 times the square root of -1, that is going to be -1. In other words, I squared is equal to -1. This is something that we probably have to remember as well. But if you know that I is equal to the square root of -1, then you should be able to know that I squared is equal to -1. Now, I leave it up to you as an exercise. What do you think I cubed is going to be? I to the 4th power, and so on. And when you do that, you'll notice an interesting pattern. Alright. The addition of complex numbers. Now, adding complex numbers is very easy. Let's just look at the first few examples here. Now, is there anything besides 1 outside these parentheses? No, there's nothing outside the parentheses that we need to distribute. And so basically, do we need the parentheses? No, we don't need them. So we can basically write A as 6 plus 5i plus 4 minus 7i. And what we want to do now is just basically combine like terms. Here we have 6 and 4, which is 10. And then we have 5i minus 7i. Do the arithmetic, and that's going to be -2i. Simple as that. We just added these two complex numbers and it gave us this. Okay, I think we can do another example. Let's do B. So B, again, is there anything outside these parentheses that I need to distribute besides 1? No, there's nothing that we need to distribute here. So basically, we don't need the parentheses. -5 plus 3i plus -3. Well, that can just basically be -3 minus 3 minus I. Okay, again, we want to combine like terms. Here we have -5 minus 3 is -8. And then 3i minus I is going to be positive plus 2i. Again, we're treating I like a variable, and so that's how that works. Alright. So we added complex numbers, now we're going to subtract complex numbers. Now take a look at this. Does this parentheses have anything on the outside that I need to distribute besides a 1? No. So do we need this parentheses? Not really. Just bring everything down except for the parentheses. So we have 12 minus 13i. Now looking at the next parentheses, you notice that I have negative on the outside, and this is basically just a negative 1. And so this negative 1, we need to distribute that negative 1. And so negative 1 times negative 5 is positive 5. Negative 1 times 4i is negative 4i. Okay, so every time you see a negative in front of the parentheses, you have to distribute it. It's very important. Alright, now we just basically do the same thing that we've been doing. Combine like terms. 12 plus 5 is 17. Negative 3i minus 4i. Well, that's going to be negative 17i. Alright. So there's just a little bit of added work when you're subtracting complex numbers. Don't forget to distribute the negative 1. And here's some added practice for you. Okay, now we start getting into multiplying complex numbers. So let me rewrite this again. Notice the operation in between is not addition, it's not subtraction. If you don't see anything, it's going to be multiplication right there. We're multiplying these complex numbers. Now, how do I multiply complex numbers? Well, you're basically distributing. And this is what I mean. You're going to take the 2, multiply it to the other parentheses, distribute it to the other parentheses. So 2 times 4, that's going to be 8. 2 times negative 5i, that's going to be negative 10i. Okay. Again, we're going to take 3i this time and distribute it to the to the other parentheses. So 3i times 4, that's going to be 12, positive 12i. 3i times negative 5i, negative 15i squared, because I have I times I. 3i times negative 5i, negative 15i squared. Okay, now all we have to do is just combine like terms. 10i plus 12i, that's going to be plus 2i. So we have 8, bring that down, and then we have negative 15i squared. Now let me ask you this question. Is that all I can do? Can I simplify it further? Remember this? Does that look familiar? I squared. It should. I squared, remember, is equal to negative 1. I is equal to the square root of negative 1. I squared is equal to negative 1. And so we're going to use that to simplify it even further. And so what I mean is, let me bring everything down. I squared becomes negative 1. So we no longer have I, we replace it with negative 1. And now take a look at this. Negative 15 times negative 1, well, that basically becomes positive 15. 8 plus 15, do a little bit of math, and that's going to be 23. 23 plus 2i. So, whenever you multiply complex numbers, you're going to come up, you're not always going to get I squared, but most of the time you're going to get I squared, and you have to remember that I squared is equal to negative 1. Which means that, notice here, I can write this complex number where I have my real part, which is 23, and my imaginary part is 2. That's something important that we always want to write our answers in. Again, here is my real part, here's my imaginary part. My imaginary part here is negative 17. And the same thing with these first two examples. My real part here is 0, my imaginary part is negative 2, real part is negative 8, and imaginary part is positive 2. So whenever you're doing operations on complex numbers, your answer always has to be in this format, where you can tell where your real number is and where your imaginary part is. Okay, let's do some more examples. Let's do these right here. Okay, so let's take a look at this. Here, again, we want to distribute, so we're going to take the 5. 5 times 5 is 25. 5 times negative 3i, that's going to be negative 15i. Now we're going to distribute the 3i. 3i times 5 is positive 15i. 3i times negative 3i, well, that's going to be negative 9i squared. See, we have I squared again. So let's go ahead and simplify. We have 25. Negative 15i plus 15i, well, that basically is 0. And then we have negative 9. I squared, again, remember, is negative 1. And so 25 minus 9 times negative 1, that's basically 25 plus 9, which is equal to, do the math, that's going to be 34. Isn't that interesting? Even though we multiplied two complex numbers, it turns out that our answer came out as a real number. By the way, this still has an imaginary part. What's the imaginary part? Well, we don't see it, but it's basically 0. This can be written as 34 plus 0i, where 0 is my imaginary part, and 34 is my real part. Okay, so maybe this was just a coincidence. Let's see what we get for this one right here. 8 plus I, 8 minus I. Distribute the 8. So 8 times 8 is 64. 8 times negative I is negative 8i. Okay, distribute the I now. I times 8 is positive 8i. And I times negative I is negative I squared. Okay, so we're going to have 64 negative 8i plus 8i. Well, that becomes 0. Then we have negative, we can just write this as negative 1. And then we have I squared. I squared is equal to negative 1. And so take a look at this. Well, why do I have two negative 1s? Well, this negative 1 is basically that right there. Negative 1 times I squared. And then I squared is equal to negative 1. Alright, so this basically becomes 64. Since I have two negatives here, it's going to become positive. 64 plus 1, which is equal to 65. Again, isn't this interesting? We have a real part, and then again the imaginary part is 0. Now, why is this giving us real numbers only? Well, what do you notice about this? Here notice that I have basically the same numbers, except the sign of something is different. The real part is the same, so the real part is exactly the same, nothing changes, but look at the imaginary part. Here my imaginary part is 3, and here I'm multiplying by the opposite of the imaginary part, which is negative 3. Here my imaginary part is 1, and notice my imaginary part becomes negative 1. So could there be a pattern going on here? Very interesting. let's take a look at this. The complex conjugate of a plus bi is defined as a minus bi. For example, the complex conjugate of 2 plus 3i is 2 minus 3i. So take a look at that. Isn't that what we have here? As you can see, the real part stays the same, and each of these, this, and this as well, they're all called conjugates, complex conjugates. Conjugates. These are complex conjugates. Why are they complex conjugates? Because the imaginary part is basically the opposite sign of the other parentheses. Here, this is positive 3, so the complex conjugate must have a minus 3 as the imaginary part. Here, it's negative 4 as my imaginary part, so the opposite is to be plus 4. Here, it's plus 1, and so we have negative 1. That is exactly what a complex conjugate is. And so, looking at number 12 real quick, a special property of multiplication of complex numbers occurs when a number is multiplied by its conjugate. Multiply each number by its conjugate, and then describe the product when a number is multiplied by its conjugate. Again, we want to multiply by its conjugate, so take a look at this. The real part stays the same, so that's going to be 2, and the imaginary part becomes the opposite. And so this is going to be plus 9i. Here, again, the real part stays the same, negative 5. The imaginary part becomes the opposite, so it's negative 2i. Okay, now there is a pattern going on here. There's a pattern, and that pattern will enable us to find the answer of multiplying complex conjugates. So let's do this again. So we're going to distribute the 2. So 2 times 2, that's going to be 4. 2 times 9i, that's going to be 18i. Negative 9i, we're going to distribute that times 2, that's negative 18i. And then negative 9i times 9i, that's going to be 81i squared. Okay, now notice, again, we seem to always get these i's to cancel out. And so we have 4 plus 81, and then I squared is equal to negative 1. And so we get that 4. Oh, by the way, I messed up here. This is supposed to be negative 81 because I have negative 9 times positive 9. So negative 81. So that means to change that, negative 81. Okay, so now I have negative 81 times negative 1. Well, that's basically 4 plus 81. And so you add those together, and we see that we get 85. Are you starting to see a pattern here? Where do we get this 4 from? And where do we get that 81 from? 4 comes from, if you look back here, 4 comes from squaring 2. So 2 squared is 4. And then 81 comes from squaring either negative 9 or positive 9. It doesn't matter. You still get positive 81. Take a look at the other ones. Looking back at here, before we added those two numbers, before we got 34, we added 25. 25, where did that come from? So it came from squaring 5, the real part, squaring the real part, which is 25. And where did 9 come from? It basically came from squaring either 3 or negative 3. If you square 3, you get 9. If you square negative 3, you still get 9. Are you starting to see the pattern here? It's going to work the same for this one. again, before we added to get 65, 64 came from 8 squared, and then 1 basically came from 1 squared. 64 plus 1 gives you 65. And so using that pattern, can we just square the real part and the imaginary part? Now this only works whenever you're multiplying complex numbers that are conjugates of each other. That's the key. You have to have conjugates of each other. Isn't the answer just going to be squaring the real part? So what is negative 5 squared? Well, that's going to be positive 25 plus the square of the imaginary part, which is going to be 4. And that is going to give me 29. Isn't that interesting? Taking that shortcut, I don't have to distribute. I can just go ahead and do the shortcut, and that gives me my answer. Now, why does this work? Well, let's take a look here. Let's prove it. Whenever you multiply two complex numbers that are conjugates of each other, is it always going to be the real part squared plus the imaginary part squared? Well, let's take a look. Again, a plus bi. How do we get the conjugate? Basically, the real part stays the same. The imaginary part here is b. That's going to be the opposite, so a minus bi. Now, let's go ahead and distribute. So we have a times a, that's going to be a squared. A times negative bi, well, that's going to be negative abi. Again, let's distribute the bi. Bi times a, that's going to be positive abi. And then bi times negative bi, well, that's going to be negative b squared I squared. Now take a look at this. That cancels out, becomes 0. So we get a squared minus b squared times I squared. Again, I squared is equal to negative 1. And so we have a squared minus b squared times negative 1. Negative b squared times negative 1, well, that's going to be positive b squared. And as you can see, whenever you multiply complex conjugates of each other, the answer is always going to be the real part squared and the imaginary part squared. There you go. We just proved that whenever you multiply complex conjugates, it's always going to be this. Alright. So we added complex numbers, we subtracted, and then we multiplied complex numbers. The last thing we want to do is divide complex numbers. Well, that's the last thing we're going to do. Alright. Here's how you do it. Basically, you take whatever's in the denominator and you multiply by its conjugate. So again, the real part stays the same and the imaginary part becomes the opposite, so negative 3i. So you always start off with the denominator. Take the complex conjugate, and now whatever you do to the bottom, you have to multiply the top to minus 3i. Okay. Now, can you see how our division problem basically became two multiplication problems? One of which we can find easily. What is 2 squared? Well, that's 4. What is going to be 3 squared? Well, that's going to be 9. So we found this easily, 4 plus 9. Now all we have to do is just basically distribute the top part. Can we use the shortcut? No, because they're not conjugates of each other. And so we have to distribute the 4. 4 times 2 is 8. 4 times, and we can do this fast because we've already multiplied complex numbers. So 4 times negative 3i, well, that's negative 12i. Negative 5i times 2, that's negative 10i. And then negative 5i times negative 3i, well, that's going to be positive 15I squared. Okay, let's combine like terms. We have 8 minus 22I, and then I squared is equal to -1, so that becomes -15 over 13. 4 plus 9 is 13, and so 8 minus 15, well, that's going to be, do the math, -7. So we have -7 minus 22I over 13. Now again, whenever we found our answer, we always wanted to leave our answer where we can find what is my real part and what is my imaginary part. Real part, imaginary part. So same thing we want to do here. The way I want to write my final answer is by just basically writing it like this: -7 over 13 minus 22I over 13. Those two are the same thing. So now the reason I want to write it like this is because I know this is going to be my real part, and -22 over 13 is my imaginary part. So you don't want to forget to leave it in this format. Basically, a complex number can always be written as a plus bi, where a is my real part and b is going to be my imaginary part, which is what I did here. Okay, and then finally what I had you do is get some more practice with that one, and then I had you do lesson 8-2 practice. Let's see here. Let me do one more example so you can get some confidence in how to do this. 1 minus I square root of 3 plus 4I. Again, you want to take the denominator and find the multiply by the conjugate. So the real part stays the same, the imaginary part becomes the opposite, and then whatever you do to the bottom, you have to multiply exactly the same to the top. Again, we want to use the shortcut here. You take the square root of 3, square it. Well, again, square root of 3 squared, well, that's basically 3. 4 squared, well, that's going to be 16. Alright. I love the shortcut. It's just so easy. Alright, now basically the real work is doing the numerator. Because these are not complex conjugates, we have to distribute. So 1 times square root of 3, square root of 3. 1 times -4i, that's going to be -4i. Negative I times the square root of 3, well, that's going to be -I square root of 3. And then -I times -4i, that's going to be positive 4i squared. Combine like terms here. This becomes -1, so we have -4. So -4 square root of 3. Hold on. So -4 plus square root of 3. And then we have -4i minus I square root of 3. All over 3 plus 16, which is 19. Now notice, the square root of 3 is not a perfect square, so we can't simplify any further. And again, we want to write this so that we can find my real and imaginary part. My real part is going to be -4 plus square root of 3 over 19. And my imaginary part is going to be -4 minus square root of 3. I goes on the outside over 19. Now why did I write it like this? I basically factor out the I, because when I distribute it back, it gives me -4i times minus -I square root of 3. But the reason I wrote it like this is because my real part is this, And my imaginary part is this, whatever's next to the eye. Okay, that's it. Thank you for watching.